Welcome. In this mini lecture, we're going to cover the first key idea from Chapter 5, contrapositive proof. So, if we're given a statement of the form P implies Q, the contrapositive of the statement is not Q implies not P. It's a fact that a statement and its contrapositive are logically equivalent. Take a moment to go prove this to yourself. Go, write a truth table. Go ahead and pause the video. You can do this. Now, sometimes it is easier to prove the contrapositive of a statement instead of the original statement we're given. So, the outline of a proof of this form will look like we have a theorem, if P, then Q. So the proof, we indicate to the reader that we're going to do it by contrapositive, and then we'll suppose that not Q is true, and go through our logical steps until we get to the conclusion that not P is true. So let's take and look at an example of this. We're going to let x and y be integers, and we'll prove that if x, y is odd, then both x and y are odd. So let's begin by taking a moment and writing out the contrapositive. So the contrapositive of this statement would be if x or y is even, then xy is even. As you can see, this is probably going to be an easier statement to prove. So let's go ahead and prove our statement by contrapositive. Again, we're going to tell the reader that we're going to use the contrapositive. And so we will suppose that x and y are integers such that x or y is even. That x or y is even, that or is a hint to us that cases is probably going to be a good route to go. So let's consider case 1. And we'll suppose that x is even. By definition of even, we can write x equals 2k for some integer k. Now, we can consider xy, which would become 2k times y, which would be 2 times ky. Since the integers are closed under multiplication, ky is an integer. Hence, xy is even. Now case 2, what will case 2 look like? Well, if we suppose instead that y is even, then by definition of even, we can write y equals 2m for some integer m, and now xy equals x times 2m, which is equal to 2xm. And again, since the integers are closed under multiplication, xm will be an integer, and hence xy is even. we get to the same conclusion. Now, if you observe in these two cases, they're essentially the exact same thing. Whether x or y is even doesn't matter. It looks the same. So, one way that we can sometimes avoid writing out both cases that are identical, with the exception of the name of the variable that we're allowing to be whatever, have whatever property that is, one way we can do this without writing out both cases is instead to write the proof in this way. When we get to the point when we're going to write cases, we'll say, without loss of generality, suppose x is even. And then continue in the same way that we did above. And so because the cases are exactly the same, whether we choose x or y to be even, this without loss of generality allows us to cover both possibilities in one single case. Be careful when using it that you aren't over-generalizing your proof. This can sometimes be tricky, so if you have questions, make sure you come talk to me. Let's do one more. Let's show that for any real number x, if x squared minus 5x plus 6 is less than 0, then 2 is less than x is less than 3. So, again, let us write the contrapositive statement. Which would be if x is less than or equal to 2, or x is greater than or equal to 3, then x squared minus 5x plus 6 is greater than or equal to 0. Again, this sets us up for cases. So for our proof, we'll again go by contrapositive. And we will suppose that x is a real number such that x is less than or equal to 2, or x is greater than or equal to 3. So case 1, let's suppose that x is less than or equal to 2. Now, x minus 2 will have to be less than or equal to 0. Also, if we were to subtract 1 from each side, we would have that x minus 3 would be less than or equal to negative 1. Thus, x minus 2 times x minus 3 would have to be greater than or equal to 0. Why is this the case? Well, think about it. This is less than or equal to 0. This is also a negative because that will be less than or equal to negative 1. So, in the worst case scenario, our first term is 0 times something that's negative, which would be equal to 0. If our first term is less than 0, it would be negative, and again, another negative, and we know that when we have two negatives, we get a positive. So, our statement holds. Case 2, we can suppose that x is greater than or equal to 3. So now x minus 3 would have to be greater than or equal to 0. And x minus 2 would have to be greater than or equal to 1. Thus, we would have x minus 3 times x minus 2 would have to be greater than or equal to 0. In this case, each of our terms are positive or 0, which again guarantees that the product is greater than or equal to 0. In all cases, x squared minus 5x plus 6 is greater than or equal to 0. Now, again, I didn't say this when I started the proof, but how did I know to start with x minus 2 or x minus 3? I mean, we had two things that we were given, but ultimately, remember, we were trying to show that x squared minus 5x plus 6 was greater than or equal to 0, which its two factors are x minus 2 and x minus 3. So now that we've completed the proof in both cases, we can put it down in our box and do our happy dance. Take a moment and think about why using without loss of generality is not appropriate in this situation. It's not appropriate because x is less than or equal to 2 and x is greater than or equal to 3 are very different statements. It's not like saying one or the other is even. These are two very different statements. We must consider the cases independently. That's all for now. Have a great day.